Hello everyone, and welcome to the first video on my new channel, where I'll walk you through my personal trials and tribulations as a young and budding electrical engineer, as well as share my personal project with tips and tricks I've learned from others or discovered along the way. I wanted to make this channel so that people like myself could share their ideas and projects without the sort of intimidation that other channels may sometimes provide. I mean, don't get me wrong, I love learning the hardcore science after the fact, but I've always needed that simple metaphor or demonstration to really kickstart things in my brain. This is sort of an experiment for me. I really wanted to see if a channel like this is something that people could get behind. But anyway guys, I'm Lyle and thanks for watching. In this video, I'm going to detail the design process and assembly of my very first vacuum tube stereo, and I'm honestly really very excited to share this with you all. I spent a lot of time working on this. I think from the research to the design, and then research because I messed something up at the bench. Design, procurement of the parts, assembly, testing, redesign because I messed something else up. To final, this isn't the final product, but to the end of, this is the point I'm at now, probably took 5 or 6 months. So this has been something I've been doing for a long time, and I'm really excited to share it with you all. I'll cover specific design choices I made, schematics, the assembly procedure. You can't see my air quotes there. We'll talk about that later. The bill of materials, and talk about what I would do differently if I had the chance to attempt this project in the future. As this is my first attempt at a video of this nature, I guess, I'm not really sure how it's going to turn out, but as with pretty much everything I do, I'm going to give this a solid college try, so let's get into it, guys. I guess the first topic of discussion should be, Lyle, why did you decide to build a vacuum tube amp as opposed to its solid-state counterpart? And I suppose I could undoubtedly come up with some contrived BS answer involving the good old days, or back in my parents' day, they used to make things like whatever, but the truth is, guys, and I have to come clean on this, I'm a millennial. There, I said it. And one of the major side effects of my condition includes a deep nostalgia and appreciation for the technology that came before me, if that's even possible, as well as increased avocado consumption and a love for bands I didn't grow up listening to. Short story long, guys, I just wanted to experiment with the tech of old to see what it could teach me. I mean, this tech pioneered what we have today, so it is certainly interesting from that point of view. Plus, you can only learn so much by looking things up, so I decided to take a stab at improving my current home stereo setup, which I should immediately point out is pretty much non-existent, so a device that makes any sound at this point other than my terrible TV speakers is an improvement. But first, a word of warning. Any information shown in this video is purely for educational purposes. Any attempt at recreating what I show in this video is done at the user's own risk. I would not attempt a build like this without a solid understanding of safe electrical practices and the proper PPE. This device has high AC voltage as well as high DC voltages present. You could be seriously injured or even killed if you're not paying attention and make a mistake. There's not really a lot of room for error in devices like these, or at the very least, you could receive a very nasty shock, and ask me how I know about that. All right, everyone, let's get into it here. First, we're going to start with your 120 volt AC coming in there, for your standard North American power. Ideally through a line filter. I didn't end up using one in my design. I just didn't really find that it was necessary in my circuit. But coming to the input of the power transformer, right, there's actually 2 windings on the secondary. So 120 volts in AC, you're going to get 120 volts out. Passing it through a rectifying stage, you can either use a full bridge rectifier, like I did. I actually removed these 2. Or if your transformer has 180 volt plus to 180 volt minus with a center tap, you could actually just use 2 diodes and you'll get the same amount of power as you would with a bridge rectifier. Going through a couple of filtering stages. These resistors here, what I've learned is that they're only required to be a half watt on the website. However, these get very, very hot, and actually I have had to replace a set of these because over several hours of running, they will get really hot. So make sure you bump those up to at least make them a watt, just to be safe. Passing through some more filtering here, then we split into 2, not really rails, but 2 portions of the power supply, one for the left channel, one to the right channel, each with their own filtering, a 4.7K ohm resistor, as well as 2 capacitors for the to take out any remaining noise that could be on this line here. Then there's a second set of the power transformer, the EdCore transformer. I'll talk about that later. The bill of materials. We go through a full bridge rectifier. 3 diodes actually conveniently used because the full bridge rectifier, you're going to get a higher voltage when rectified as opposed to a single diode. So they actually, I believe, Brian is using these to just drop the voltage. Every diode, silicon diode, is starting off initially is going to have a drop of about 0.7 volts. So you might read, 13.5 volts, but that's a little too high for the heaters on the vacuum tube. So 0.7, 1.4, to 2.3. So it's just taking kind of the edge off for these because you really don't. It's better to run the filaments a little cooler. I haven't noticed any issues with that, but if you run them really anything more than their rated 12.6 volts, you're going to start having some issues with longevity. And as a common little trick they used to use back in the day, if you had some of the tubes, actually my two output tubes for each stage, the filament winding requires a filament voltage of 6.2 volts or 6.3 volts, excuse me. And instead of having to make an entire separate power supply for this, you can actually just place two of them in series. So you see I've done that, or Brian has done that. He's put the two 6.3 volt filament windings in series to get the 12.6 volts total, as well as the 5751s, the input tubes, which require a 12.6 volt filament. You can just run that straight off the rails there. So jumping over to the input now, or the actual amplification, I guess, you're going to have your input jack or your RCA, or in my case I actually added a Bluetooth as well, so there's some more involved over here for my final product, but this is just the basic operating principle. This is for a single channel of this, so obviously you're going to have to duplicate this top section. You have to wire this all up twice, so it definitely adds up very quickly. Coming in through a 1K ohm resistor, the 5751 vacuum tube actually has two triodes independent of each other inside of the same package. So if I grab, this is functionally the same thing. This is a 12AX7. You can actually see, if I bring that up, as I turn it, see that? This tube, as with many others, like the 5751, any of the 12AX or 12AU 7 variables of this type will have two plates, two cathodes, two grids, and two separate filament connections. So you're really getting a two-for-one, which is nice because it's great for either stereo amplification or you can do left and right channel in a single tube if you're not looking for a whole lot of gain in the initial stages, or you can do what is happening here, which is to have a single an initial amplification stage and then use the second half to amplify that signal again. So quite versatile, awesome little devices, and you end up getting a lot of space savings for using a device like this instead of having to have two separate triode tubes feeding through a decoupling capacitor, because you don't want the DC portion of these tubes to be present on the grid of your next, especially the high voltage DC, present on the grid of your output tube here, because you will kill it. So as I was assembling this and testing this, was very cautious to make sure that capacitor was in there, and that there wasn't any possible way for this high voltage DC to get to the output tubes, because you'd kill them pretty much instantly if you did that. This design from Brian, if you check out the DIY audio website, he's using a pretty creative setup here. He's using a LM317, typically uses a voltage regulator as a current source or shunt, depending on which direction of the input signal is coming into the tubes. Initially, you'll have to read his description of this circuit. He'd do a lot better job of it than I would be able to. But basically, it removes the need for you having to add a inversion tube to drive this tube, because typically you would have your signal coming out of your preamp into the first tube, and you would have to tap off of that, invert the signal to drive the other tube, because if you drove these both in the same phase, nothing would happen. You wouldn't get any amplification. So this top tube, depending on how you look at it with your sine wave, would take care of the top portion of amplification, whereas this tube will take care of the bottom portion, the negative half of your signal. That signal is then fed to the output or audio transformers, where the high impedance, high voltage, low current output of the tubes is converted or transformed into a low voltage, low current low impedance output that is required to drive the speaker. You couldn't directly attach the speaker to this one because it's a very high voltage. But even if you did attach the output of the transformer directly across these terminals, you would pull this voltage right down. And these tubes cannot support that kind of current, which is the whole operating principle of a vacuum tube. They are a voltage controlling device and not a current controlling device. Feeding into a speaker of your choice, I have a set of Clifshes that I recently bought a couple of months ago, and they sound awesome. They're perfect for this because this is only meant to drive, depending on how brutal you want to be to the system, between 5 and 7 watts is what I saw on the website, and I believe that I am getting that. These things this actually is quite loud, especially for a 750 square foot apartment like mine. We have some negative feedback here, which takes the total output of the amplifier. It lowers the total gain that you can achieve. However, it reduces the risk of this circuit, the output of the speaker developing some sort of oscillation that is then fed back into the input of the tubes, and then just causing this terrible screeching sound. And it's really bad for all of the equipment involved, the speaker, the tubes, the power supply is really going to suffer from that. So this is pretty important, that negative feedback. Also, as they describe on the DIY Audio Project's website, you may get some ringing if you hook this up backwards. So if you ground, say, this side and bring negative feedback to this side, you might end up creating positive feedback, which makes the problem even worse. I had 2 scenarios that happened with mine. One was a very high-pitched squealing, and the other was a just low, grumbly, like a motorboat, I've heard it referred to as, sound. Both very unpleasant and both very bad for the equipment. So when you notice that to start happening, if you're going to try and attempt to build something like this, just stop it, cut the power and swap the connections, either from these 2 points, or you can also try reconfiguring the input of the audio transformer. That actually is what fixed it for me. So give that a try. All right, everyone, we are at the computer. I am going to kind of roll the design changes and the sort of some of the procurement of the different parts into this section here. Not really going to follow initially that slide 1 to 5, and I am going off of the script I created, which will make this a little more interesting. DIY Audio Projects is where I have been doing my research and checking out other things on the website. This is a really cool website. They do not only your tube amp builds, but speaker cabinets. They do some phono stuff. So if you're into records, that's a cool thing. Cheap cables, cheap audio cables, and it's just a really cool website. And there's a lot of really smart people running this website. I also want to make a correction to, I kept calling this guy, I think Brian, but this is Bruce. Let me go to the actual project. Yeah, Bruce. So anytime you hear me say the word Brian, I mean Bruce, sorry. This is the page on DIY Audio that I ended up landing on. And you can see looks pretty similar to my device I ended up creating. He's got an extra sticker on there. He just used a black, an anodized aluminum black box for his enclosure. A little more simplistic than mine. Some different audio transformers in the back, but as you can see, as we went over before, here is the version 1. There's actually a couple of revisions that he made to this circuit later on, but I decided to stick with this because it was, it seemed to work fine in my testing. Here he describes the shunt regulated push-pull driver stage. And again, he's made several revisions to this down at the bottom of the page. Just improvements that he's made as he's gone along. This is a really cool, he describes things very well in this, so take a read on that if you're curious. So I want to make sure I'm not, yeah, he built it on, he goes through his building procedure as well. It's very simplistic. He's obviously assuming that just basic assembly techniques and, how to be safe in terms of clearance for all these different components. Because the last thing you want to do is blow one of these capacitors. These definitely the most expensive capacitors I've ever bought. They're very high quality, made in France. They, depending on the size you get and the voltage rating, they could be $15, $20 a pop. So you definitely want to take care when assembling this. He also goes through some actual testing and measurements. I do not possess the equipment, the audio equipment to do that. So unfortunately, I can't verify the outputs that I'm getting. All I can tell you is that it's loud and it sounds good. He shows the frequency response. Oh, there goes my AC. And I think for all of Bruce's posts to this website, he shows the updates that he's made with descriptions. And I think he said he plans to have this device in operation for between 6,000 to 8,000 hours, which is pretty impressive. The only real big downside to vacuum tubes is that they do wear out over time, as opposed to solid state, which theoretically, if you treat them right and nothing goes wrong in the circuit, they should last pretty much forever. So yeah, let's move on to the transformers. So it's very difficult or very expensive to find on eBay the exact kind of transformer that you're going to need. So this website, Edcore, I believe based out of Arizona, sells custom-made, like handmade, like to-order transformers that you can. There's probably 100 different kinds of transformers you can pick depending on the needs that you have. And this is kind of getting into one of the design changes I had to make in my circuit. In Bruce's schematic, he actually used he's using full wave rectification, which just uses 2 diodes, as long as you have a center tap that you can reference to your ground potential here. I could not find one that had the center tap with 180 on either leg, but I was able to find this one. Right, so when you go to checkout for this, you can select the impedances you want, primary impedance, secondary impedance, the voltages that you're looking for. Do you want a 40% screen tap? Things like that. I did end up using a 40% screen tap. This is also a 10-watt transformer with a primary impedance of 10 ohms, 40% screen tap. Just depending on what you need, you can pick the different transformer that might suit your particular situation. This one ended up suiting me. That I had the only real design change I had to make for that is, like I said, I actually added a full bridge rectifier here because I couldn't find a transformer with the correct voltage that had a center tap with, that I could tie to ground. I'm sure you probably could find something online, but I couldn't find anything at the time, and I was just, since it's, up to 8 weeks, I did end up waiting actually the full 8 weeks to get this product. So definitely, if you're looking to do something, it's not, too expensive either, but if you're looking to, start working on this project, you can do the design and everything else of the other portions, like the power supply. I actually built the power supply before I started the actual amplification stage, and you're going to want to get these on order as soon as possible because some people say it could take, if they're maybe a little low on work, you could have them in 3 weeks, but it took me the full 8 weeks to get them. Moving on to another website, Antique Electronics Supply. This website's really cool. It's not just for vacuum tubes. They have all the components you would need, capacitors, resistors. They also have a lot of modern devices and components here to repair them. I think there's like lasers for like CD readers, guitar equipment, just all different kinds of stuff. They have schematics if you're lucky enough to find, just opening one up, if you need a specific schematic and you're not able to find it online, you can purchase it here. Which is really cool because that's just a very valuable resource for you to have. While I'm here, I'm going to talk about matching the output tubes. So a problem that I guess kind of in the old days, people would just throw tubes into guitar amps and say, just kind of go with it. The problem with that is if the tubes aren't matched, especially in a circuit that relies on the balancing, these tubes to be very closely related, because if the circuit is always conducting, that's one of the main descriptors of a Class A amplifier, is that regardless of whether it's actually amplifying a signal or not, it is always on. So that obviously tanks efficiency. It's terribly inefficient. However, it's the response you get tends to be very linear. So the sound recreation is typically better than some of the more efficient modes of operation like A, B, and D, because you don't get that crossover distortion with just a regular push-pull amplifier like a Class AB. One transistor or two would just amplify this top portion, and then another transistor or tube would amplify the bottom portion, and that's all fine and dandy until you realize that, especially with silicon devices, they can't at the close to the zero line, they can't perfectly transfer. You end up getting a distortion because diodes and the junctions of transistors actually have a forward voltage, maybe typically less than a volt, but that problem really manifests itself in the low voltage circuits. In the high voltage ones like this, it's not as big a deal. Obviously, 0.7 volts out of 50 volts is not as bad as 0.7 volts of distortion on either side of the zero line at a 5 volt amplification. So yeah, Antique Electronics Supply was a place that I found is really high quality parts. If you're going to already spend, $100 just in just the two audio transformers, that's not even the 100 something I had to spend the actual power transformer, which again is something you could probably source from eBay or something like that. But I found it more convenient to just tell them what I needed and just have them make it and just wait. So, in transformers alone, you're already looking at $250, $300. This isn't even high price tag items. You could easily spend the real audiophiles and tube files out there would probably spend upwards of $400 or $500 just for the transformers alone. So it's a pretty good deal for what you're getting, and it's made in USA, which is pretty nice. So now I guess the next section we're going to be looking at the actual my final design, my final schematic that has incorporated Bruce's initial simple designs. So I'm going to, obviously this is the power supply here. Not much here has really changed, except in order to drive the Arduino or the Atmel 328P and the VFD. I did include just a simple 5-volt power supply here. Make sure when you're designing this that you give it room for a heatsink, because the VFD draws quite a little more power than I was anticipating. And although it does work without a heatsink, it does get really hot. And that's definitely something I would change if I were to do this in the future, is on the actual layout of the board. Just give this more space so you could put a proper heatsink on there. I wasn't thinking when I did this. It was kind of an afterthought. Oh crap, I have to make a power supply, because the Arduino breakout board does that for you, but just the chip, the 328P, does not. And I didn't remember that until the end. And obviously there's some space concerns involved. So there's a lot to think about when you're doing this. If you want to actually build, Bruce did this. He built it on perf board, and it typically with amplifiers that they did point-to-point wiring, which is totally legitimate. Obviously, you can never sell a product like that today. It's just not. It wouldn't pass any sort of modern electrical safety standards. But it is, it's something they did for a long time, and it was very effective. All right. So going on to the amplifier section, let's start with the inputs. The purpose of, I figured while I already had the Arduino in there to control the VFD, the display, I might as well use it to control the switching, so I don't have to put in different switches as I go for each input. So I got a couple of relays, each one through just a small limiting resistor. This is a double pole, double throw relay, which allows me to switch a left and a right per relay, which is awesome because I like stereo sound. So I have an auxiliary in, which is a 1/4-inch jack, a header, which I use to connect the Shure Bluetooth audio receiver, and then the signals come in here. And same goes for the RCA. I wanted to add, the initial plan for the RCA jacks was to simply, if I ever wanted to hook up a very low signal device like a guitar or a phono input, you really should probably amplify that a little bit more. It's a very low level signal if you're running it directly from the needle on the record or from your guitar. So the plan initially was to somewhere along this line, either before it got to even the relay or before it came to the input here, that I would add some sort of amplification, but that never really came into fruition. So this input, the RCAs are equivalent to the aux in and the Bluetooth. As you can see from my global points, which basically, if I use these connectors, anything labeled with this, example left 12 volts heater comm, anything labeled with this in the circuit is going to be electrically connected to it. So this way you don't have to run a wire for every one all the way down to here. It cleans it up a lot, and it just makes it easier for your, when you do a personal QA, just looking at this, making sure that everything's connected right and you're not trying to trace wires all over the place. I have done that in the past, and immediately regretted it when I tried to find out a problem. So any 3 of these inputs can be switched via the Arduino into the input, and pretty much here is the same thing as Bruce showed. I'm just using here. There's a 2-pin standard pitch header connector, which I don't actually attach headers to. I just use them for convenient points to create the holes with the vias in the circuit board. As you can see, this is all very similar. This is for one channel, and this would be for a second channel. And then here we're going to the output or the input of the audio transformers. There would be, not shown here, the 2 windings of the transformer with the core. Here's where the secondary connects. And this switch that I added allows me to switch all 4, so left plus, left minus, right plus, and right minus, outputs from both of the audio transformers. Allows me to switch between the speakers, all 4 of them independently, between the speakers and the headphones out, which is awesome because as much as I like blowing my neighbors into the 7th dimension, I do like having a place to live. Over here, this is just power connection. Just I wanted to isolate them again to separate them into their functional components on the circuit, on the schematic. And it, like I said, it also makes it just easier to look at and troubleshoot. The Arduino, pretty standard setup. Got to pull the reset pin high so it doesn't automatically reset. The 16 megahertz crystal with the loading capacitors, the button that I used to change the inputs, the 7 connections that are required for the vacuum fluorescent display, and the 5 volts and the heater comm. I'm going to call it local. It's not the same ground as this. They have to be separate, and I'm going to actually talk about that right now. You can't, because the transformer, if you look back at the schematic, because there's 2 windings of the transformer on the secondary, when the input is coming in from the line, from the wall, these windings on the secondary cannot be, like, if you can't call this ground and then run it and directly connect it to this ground here. You could connect them together, but the problem ends up being pulling up the data sheet for the value I want you to look at here is the peak heater cathode voltage. A typical value is 90 volts, but 100 volts is the absolute maximum value, and that is on the diagram. The cathode looks like a C. This bottom portion here, there's actually a heater in here, and what they're saying basically is if the heater or the cathode, either one, if there's a difference of more than 100 volts between these two, you're gonna have you're gonna kill the tube. I'm not sure of the actual the full details of the terrible destruction of the tube, but the problem with tying the 2 typically isolated grounds together is that you're going to be ending up putting that very tiny space between the heater and the cathodes. You're going to be putting maybe 80 volts initially when you're not running anything, and you're like, oh, that's fine, I can connect the 2. But the problem is, when you're amplifying these signals with vacuum tubes, you're taking 1 volt in from the Bluetooth or from your phone and amplifying it at that position in the stage, in the amplification. You could be swinging, if your center line is 80 volts, you could be swinging up and down 30 to 40 volts after you're amplifying it. So obviously 80 plus the 40 is you're going to get 120 volts, which is over the rating for the heater to cathode voltage. So don't be misled by that, as I was tempted to do. And of course, the Arduino doesn't care, if you're feeding in, I say plus 5 volts here, but in comparison to the circuit, the main circuit ground, that could be 80 volts, but your heater common, the other ground, could only be 5 volts less. So as far as the Arduino is concerned, there's only 5 volts across it. The Arduino doesn't care as long as it sees 5 volts. You just have to be careful when you're designing this and assembling to make sure you don't you don't tie anything together that shouldn't be there. Something else I'm going to say is that when you're doing electronics, like your best friend for anything is going to be the data sheets of the components you're trying to use, because they tell you all the ratings, typical voltage, and also an important column is absolute values, because you definitely don't want. They're basically telling you if you exceed these, you're probably going to kill it, and it's not going to be our fault. All right, so the next thing we got to talk about here is the bill of materials. But before I do that, I'm thinking I'm going to split this video into two parts. It's already a half an hour long, and in that video, I will show you. I will do a demonstration of the final product, as well as show kind of detail the assembly procedure that I had to go through in order to get this done. Obviously, this was built before I started filming this, so unfortunately, I can't show you like a time lapse of me assembling it. But it took, like I'm showing here, several hours, maybe 50-50 research and building and designing and testing. So starting off, we have the EdCore transformers, $60 for the pair of output audio 10-watt transformers, as well as $80 for the power transformer I ended up using, which brings a total to $140. From Antique Electronics Supply, the total bill ended up being $250 because I had to do a reorder, because I think I ended up blowing a couple of tubes that I had to reorder. So I only ended up using about $200 of those parts, but the total bill for that was around $250. The enclosure I got off of eBay, it was $90. That's very, very expensive. You can buy an anodized aluminum chassis for $10 or $20 in the right spots. I just like the way that the wood, the maple enclosure looked, and I figured if this is something that I want to show off to people, that I should go with a material and a design that looked really good. The only concern, as I'll mention later, during my assembly procedure, is that it's very thick wood, and I don't really have the tool. I have a couple of drills and files and stuff like that, but I had to do some skullduggery and trickery to get it to everything to actually fit in there and still look half presentable. I'm not totally 100% happy with the way it ended up coming out in some of the locations, but like I said, I'll talk about that later. From eBay, I ended up finding the vacuum fluorescent display for $20 or $30, I think. It's a pretty cool little display. I think it came out of one of the old cash registers. When this is something you'll remember back in the 90s. All the cash registers used to have, because they're similar to vacuum tubes, but they require a very low voltage. So they were kind of a transitional period between 15-20 year period where they were very popular. And I just figured it gave the final product this sort of retro overall look. I know some hardcore enthusiasts might not agree with my design choice there, but I thought it looks cool, so I used it. So the eBay total ended up being $50 between that and the Arduino component, the Atmel 32AP. I bought a set of those with they included some capacitors there, but they were if I recall correctly, the Mylar type capacitors, which just don't. I've always had issues with those with the Atmel 32P. So I just threw in some ceramics that I had lying around. I also made an order from Jamico for some of the more obscure components that I couldn't find on Antique Electronics Supply. Some of the switches, the light, the indicators. I'm sure I could have found them on Antique Electronics Supply, but they were probably a little too expensive, so I decided to go with the Jamico option. And finally, Easy EDA, where I designed and ordered my circuit boards from. They're $16 a board, and that's quite expensive, actually, compared to if you keep within a certain size, a couple of centimeters by a couple of centimeters, you're only paying $2 for a fully designed 2-layer circuit board. That's crazy to me. That, in college, I was really focused on finding ways to how could I manufacture my own circuit boards at home, and I kind of feel like that's a waste now because it's so cheap. Even with the expedited shipping, which you'll have them in a week or less, typically between 5 and 7 business days. If not, it's 2 to 3 weeks. But still, that's $50 for actually 10 in total circuit boards, because they make them in batches of 5 for you. $50 for these really large circuit boards, are very high quality. I'm very impressed with the service. I would definitely check Easy EDA out. The only problem is that the schematic, the design software that you use is obviously, it's a free software that they're including. It's a perk that they're allowing you to use this service. So there's not a lot in terms of QA when you're going through the design rule checking is not really that great. It's just going to tell you it's not going to tell you anything really specific that might be wrong. So you really got to make sure you're paying attention when you're doing this. However, Easy EDA, they allow you to upload your own Gerber files. So if you want to if you have like Eagle or National Instruments, some of those really expensive softwares, if you do happen to have access to those, you can do all your design in those softwares and then just upload the Gerber files to Easy EDA and just get the cheap circuit boards from there, which is a really cool option for those that have access to the more expensive software. Which brings the total to roughly $690, $700. I didn't include my time. Like I said, probably 60-40 or 50-50 build and research. So if I were to do this again, obviously it would take me a significantly less amount of time to actually assemble this product, because now I know kind of the tricks and the pitfalls that you're going to encounter. If it was a completely different type of design, I'd have to do the research and all that over again. But you can see this is not a very lucrative business. You know, if you're going to make something like this, to buy something like this, you can see why people would charge you $2,500, $3,000, $4,000 for a device like this, because it takes a very long time to put all this together. So a lot of it's just going to be in the labor, let alone the fact that you have to spend hundreds of dollars on just specific components for this. And at the bottom, you see that anything marked with a star that was the market price, or the price that I was able to find these components at the time. You may be able to find something cheaper, or get a bundle deal for some of these things. Some people might sell like partial kits, like tubes and transformers or something like that. So your mileage may vary on that. And I guess with that being said, I'm actually going to split this video into 2 parts, because it's taking a very long time to show all the things I want to show. If you would prefer that I show things in a more condensed format, 7 to 10 minutes per video, let me know in the comments. I'd love to hear it. I don't know. Me personally, I love sitting down and watching these 2-hour videos from people like Mr. Carlson's Lab, Brad the Gitologist, Blue Glow Electronics. I really love watching the entire detail that they go through when they're talking about all their designs and their assembly and everything like that. And my only main gripe with these 7 to 10 minute videos is you don't have a lot of time to really get all that detail in there, which is the stuff that I really strive for. So if you would prefer to see the 7 to 10 minute clips, or even to see a video like this, that is potentially 35, 40 minutes in total, to be condensed down into 5 or 6, maybe episodes, you can call them, let me know. But anyway, guys, thank you for checking this out. In a couple of days, I'm going to have the next section of this out. So thanks for watching. While I have your attention, I would like to point you towards my other YouTube channel, where I'm doing covers or otherwise with a couple of friends, and my family have also helped participate in this. So yeah, I got a couple of videos out. Check it out. I had a lot of fun making them. A similar sort of vibe what I am having for this channel, where I'm doing this to document what I ended up doing, as opposed to trying to remember 20 years from now if I ever want to pull it out and try to fix it. At least I'll have this video, right?